Good. So today we have Yoram's third and last talk on formation of hot Jupiters.
You may change your mind after. So, well, thank you all for coming on such a beautiful morning after an after party for maybe the fourth talk on hot Jupiters. I hope not to repeat what other people have done. Originally, I was planning to review formation of hot Jupiters, but since we've heard so much about it, I'll sort of fill in some of the extra things which I think hasn't been talked about, and then focus mostly on what I've worked on with hot Jupiters. Is this on? Okay, is it better?
Yes.
Okay. We've seen this period mass diagram from exoplanets.org millions of times before. And this big red splotch is hot Jupiters. There's a clear clear splotch of planets here. When Scott showed you his plot, he had a much smaller splotch, and that's because he was just focusing on RV planets. This shows everything, including transits. So you may say, oh, it's obvious, there's a huge population of hot Jupiters here. It's a distinct population from the cold Jupiters and from the Kepler planets. But it's actually not so clear because there's very strong selection effects for detecting them, of course. They're very close to the star. Is this really a population of a separate population? So Scott expressed skepticism. I think recently, in the past, about 2 months ago, there was a very nice paper by Saturn, which actually shows, in my view, quite convincingly, that there actually is a distinct population. So what these guys did is they just focused on Kepler detections of giant planets. By detections, I mean Kepler candidates. So they looked at 129 Kepler giant planet candidates, and they followed them up with RV. So it's basically, there's very little selection function involved. It's just the only selection criterion is that it's a Kepler planet with a candidate. So there shouldn't be, they can correct for any biases. And so they followed them up with RV, and what they found is around 50% of them, of the Kepler candidates, were false positives. So it's important to remove those false positives to see the underlying shape. And so this is the shape of the occurrence rate of hot Jupiters that they found. Yes? 50% of the hot Jupiters were false positives. It's a big problem for the Jupiters. So this shows the occurrence rate after correcting for the fact that the probability of transit is after correcting for the probability of transit. So this is the intrinsic occurrence rate of giant planets as a function of period. And I think this is a beautiful plot. And this, I think, is the first time that's actually been shown convincingly that there is.
How do you read this, Yoram? Each number here?
Each
is the fraction of stars that have hot Jupiters.
Exactly. Intrinsically. That's right. After correcting for selection effects.
So what the numbers of this model?
Okay, so this is 0.1%.
Okay.
This is 0.1%. This is 10 days. So this bump is the hot Jupiters.
Okay, so if I sum up all what you call hot Jupiters?
If you sum up, let's put that number next, it's 0.5%. So 0.5% have hot Jupiters. And this is also, often people are, well, one of the strongest correlations of all is the metallicity giant planet relation. That more metal-rich stars tend to have more giant planets, but this doesn't have that. Well, this is focusing Kepler is focusing on typical stars. So typical stars have around 0.5%. 0.5% of them have hot Jupiters. Yes?
To me, it looks like it's not really a separate population. It's just that one point at the bottom is kind of obscure.
Well, to me, okay. So you're free. To me, it looks like there's a bump here. If you try to fit it with, you can fit it with two distributions. It seems like it's better than a power law going through.
And warrant for that 1 point?
Well, this point and this point, and this is falling down. So you're free to take this for
that's okay.
for what you want.
It's a log scale.
Yeah, it's a log scale.
It's a log scale. It's really hard to make that point go up. It's not like a data point that you can move.
Exactly. Exactly. Theorists love just throwing away data points. And I do that too. So. Oh yeah, well, so and this is also looks quite different than the other lower mass Kepler planets, where they tend to rise at around 10 days. Seems like a distinct population in a closer planet.
Can I ask another question?
Yes.
Somewhat imprecise question. How does this jive with the 15% number of hot Jupiters that we've heard previously?
No, we never heard that.
No.
So people say 1%, that's usually biased by metal-rich stars, or 0.5%. So it's 15% might be the Kepler. 15? Yeah, so that's sometimes the Kepler, okay, yeah, it's not, it's just remembering. Sorry, okay, I forgot my next point. Originally I was going to go through in detail all of these mechanisms. I'll sort of skim through go through them at different speeds. So the basic mechanisms for getting hot Jupiters, these are all the competitors. We still don't know who wins. So there's the disk migration, then there's a set of 3 high E migration scenarios. Boaz talked about high E migration, and then there's in situ formation that could form in situ. I actually probably won't talk much about in situ formation. You can ask me questions at the end. It's only become popular recently. Okay, so very briefly, I'm going a little fast now because we talked before. Disk migration. So the idea is that you form the giant planet out beyond the ice line at a few IU. It probably opens a gap in the disk. Depends a bit on the viscosity in the disk, whether it does or doesn't. But then if it opens a gap, then it's thought that it will migrate into the star on the lifetime of the disk, the viscous time of the disk, which is around a few million years. So there are, I would say, 3 difficulties with this scenario, 3 principal difficulties, and I'll outline what I think they are. Although it's still a possibility. Even though I'm giving difficulties, I don't want to say it's impossible. So one question is, why do the hot Jupiters stop where they are? If you have planets that migrate in a disk, you would expect that it would go all the way, it would migrate towards the star until it's tidally shredded by the star. So we can ask, how close does it have to get to the star before it's tidally shredded? So the answer to that question is when the tidal force of the star is bigger than the self-gravity of the planet. And we can easily calculate that, and we've calculated this before. So the tidal force on the planet is just the gravity on this edge minus the gravity on this edge. So that's gm star over a plus r squared minus this, which you can Taylor expand to be to the leading order in r over a to be this expression. It's a tidal force squeezing the planet apart. And then the self-gravity of the planet is trying to pull it together. It's just gm over r squared, the force per unit mass. So if you equate both these two, you can find the critical semi-major axis, A, where tidal forces are just balancing self-gravity. So if I put a planet inside of A, Roche, it's called the Roche radius, it'll be destroyed by tides, and outside it can live fine for a given mass and radius. Another way of expressing this is that for a given mass and radius of the planet, this is where the planet fills its own Hill sphere. So people have done fairly careful calculations for different density bodies. What's this A Roche, and that's where this 2.2 comes from. I think it's for assuming the polytrope for a Jupiter. Okay, so you expect that the planets would migrate until they hit A Roche, and then they'd be destroyed. So we can ask, where are these planets relative to the A Roche? So I can plot, I know the these are actually, now I'm just plotting the transiting planets, again, period versus mass. And I can plot where the line of the Roche line is. This is the line inside of which the planets would be tidally shred. And we see the planets lie nowhere near that line, right? They're far away. So it seems really surprising that they'd stop here, when they could go all the way. They could, if they're migrating, they could migrate all the way to this line. An interesting fact, which I'll come back to in a second, is if I plot twice the Roche radius, it actually does seem to agree pretty well with the inner edge of this population. So the question is, how is migration stopped? If it's not stopped under this scenario, if it's not stopped by tidal forces, why don't these planets just fall into the star? Why is there a separate population of hot Jupiters? So one possibility is that maybe there's a cavity in the disk. It's magnetosphere of the star opens up a cavity in the gas disk, so all the planets come into the cavity and then they stop there. But then that would predict that you have a huge population. This is from a population synthesis model of Ida and Lin, where they put all the physics in including a cavity of the disk, and then they see some of the planets migrate inward, but then you have a huge population of planets inside the cavity. So it doesn't really explain why you get a subtle pileup.
Why are there planets?
Okay, so we have to stop the planet somehow. So if you make a cavity in a disk, so the planets are migrating along with the disk. Once there's no disk anymore, they don't migrate anymore.
So why are there planets in the cavity? Or just you mean at the edge?
Just in the inside of the cavity, that's right. Yes.
Why would the cavity be exactly at the same semi-major axis for all stars?
So that's a good question. So what they say is that it's set by the rotation period of the stars. It's the co-rotation. If it is magnetospheric truncation, then it would be co-rotation with the spin of the star. The spins of the stars are sort of in a narrow range of young T-Tauri stars, but they're actually, I think that is actually another problem, that it's too wide a range of spins of stars to give a sharp enough cutoff. But there are ways out. Okay, so another two, I think, increasingly severe challenges to the disk migration. One is the Rossiter-McLaughlin results that we've seen before. So ignore for a second the y-axis, ignore the y-axis. This shows the results of the Rossiter-McLaughlin, which remember is the difference between the orbit of the planet and the spin of the star, actually projected on the sky. So what you see, many planets are orbiting in the same sense with this small lambda, in the same sense as the spin of the star, so the orbits are aligned with the spin of the star, but many are also misaligned. And it's very difficult to get planets, under the disk migration scenario, it's difficult to get planets which are misaligned with the star. Because you expect the disk should be aligned with the star, because the star forms out of the disk, and the planet should be aligned with the disk, because the planet is the disk, so therefore you expect the planet should be aligned with the star. So how do you get these guys up here? So this is usually, the most frequently quoted argument against disk migration, but there are caveats to this argument because no one can explain, under any mechanism, nobody can explain these results. What's particularly surprising about the Rossiter-McLaughlin results is that the ones that are misaligned are in the upper half of this plot, and now the y-axis is the effective temperature of the star. So hot Jupiters around hot stars tend to be very misaligned, or the misaligned ones tend to live around hot stars, and the aligned ones tend to live around cold stars. And this transition of stellar temperature is actually where the star has a convection zone, an outer convection zone, so it might be related to the dynamics of the star. And also there are, within people who advocate for this disk migration scenario, some people have found mechanisms to misalign, for example, the star with the disk, for example, with magnetic fields. So it is a possibility. I would say no one can explain this, so it's not, it's just a puzzle. So this is what I think is the strongest argument against them forming in a disk. I don't think this has been mentioned before, which is that hot Jupiters are alone. So here I'm plotting, I just take it's the same planets from exoplanets.org, and I color code them based on whether they're singles or whether they have a companion. So the empty circles are singles, and the outer ones have companions. You see all these warm Jupiters out here, many of them have companions, and even these cold Jupiters, many of them have companions. When you look at the hot Jupiters, I think this is very distinct. Have a huge almost virtually all of them don't have companions. And in the disk migration scenario, it's very unnatural to have a population, if they're migrating a disk, why would the population that ends up close to the star be alone? Often in migration scenarios, you get planets that move together and they capture into resonance. Many of these guys, the warm Jupiters and the cold Jupiters, do have planets that are caught in resonances. Something like 20% of them of these cold and warm Jupiters have two Jupiters and 2-to-1 resonance typically. But these hot ones are almost always alone.
Yoram?
Yes.
I'm not sure it's a problem because maybe the formation of high Jupiters relates to some very fast migration in some sense, and maybe you could just kill all the planets before they actually just into the star or something. Could be something.
Well, so you're saying these guys are a different population?
No, because
Did they come from fast migration?
Yeah.
But then what about?
Then multiple planets, for example.
Well, I mean, if you're migrating very fast, you have to just have one single planet coming in, and no other planets are coming in along with it. So why would that happen? So, well, do you think that these guys migrated, for example? Or you would say these guys formed in situ?
I don't know.
And there's an I guess one would have to explain why is there a separate mode of fast migration? Why these guys presumably form, and under this scenario, it's a unified scenario. Everyone forms in a disk. They all migrate. So you need some extra physics of migration to explain why some of them migrate fast and some of them stay in a disk.
Well, it depends on the disk parameters and the planet.
Okay, maybe you can cook something up.
Yeah.
Yes.
Sorry. I think very recently, I mean, people have been saying that for years that computers are usually.
I know what you're going to say, and come back to that.
Oh, you're
So
gonna
people have measured companionship
Okay.
of the hot Jupiters, but I'll come back to that at the end of the talk. Yes.
Do you know something about very far out companions? So if they
That's what I'll come back to. So this is just taking in the exoplanet.org archive, looking at the singles and multis. If I don't get to it, please ask again before a minute, because I really want to say. Okay. Okay. So the second category of migration scenarios is the high eccentricity migration scenario, which Boaz Katz talked about. And just to very, very briefly review, you have a planet, Jupiter, forming from a star beyond the ice line at a few AU. It's perturbed by either a stellar companion or a planet companion. This guy's eccentricity is excited by gravity from the star or the planet. It gets extremely high eccentricity, so its periapse comes very close to the star. And when its periapse comes very close to the star, tides on the planet start acting, and they circularize the orbit of the planet. Okay. There's two immediate predictions of this these types of scenarios. There are also more predictions, but two that immediately pop out that, for me, make these scenarios very attractive. One is that it immediately explains why hot Jupiters tend to be lonely, why they don't have companions out to sort of these distances. This should be pretty obvious why they should be lonely, because you have a hot Jupiter which is screaming through the inner planetary system. Any planet in its way would just be ejected from the system. It has a very high eccentricity. So it just removes everybody else from the system. Yes?
Does disk migration do the same thing? Because the hot Jupiter still has to migrate into the disk.
Right, but there'd be also, so you expect there'd also be planets following on its tail. If one's migrating, the other's migrating. And if you need, the migration, you need also migration to be an efficient process to have so many hot Jupiters. So you expect in this scenario, you expect lots of Jupiters to continually flow through. So why, when you take a snapshot at the end after the gas disk goes away, you're just left with one right very close to the star. Okay, so a second immediate consequence of this type of scenario is this twice Roche radius. So it comes out very naturally. So how does that work? So the reason is that in the second stage of the high migration, so when the peri has come now close to the star, and now the star, because of tides, is circularizing the orbit, throughout that process, angular momentum is conserved. Right? Boaz talked about that a lot. So angular momentum of the planet is conserved because it's tides in the planet which is causing dissipation. So you can't lose angular momentum. Okay, and just from saying angular momentum is conserved, what we can say is that the most extreme hot Jupiters, the ones that come closest to the star, their peri, when they come closest to the star, has to be at the Roche radius. Those whose peri is less than the Roche radius will be destroyed, probably. And so the inner edge is probably would be ones that come just to right at the Roche radius. Right? So it's when their peri is at the Roche radius. So if their peri is at the Roche radius, we can use that to figure out their final semi-major axis. Okay, so we just equate the initial L to the final L. Before tidal circulation to after tidal circularization. So after tidal circularization, this, what's in the square root, is A times this, and E is 0, so it's just A final. And then before you start tidally circularizing, what's inside the square root is the initial A times 1 minus E squared. Then A times 1 minus E is just the peri distance. Right, that's R peri. So it's R peri times 1 plus E. And then we know E has to be very close to 1, because if we're going to start a Jupiter here and get it close to the star, we need E's of 0.97, that's 0.98. So this is around 2. So if R peri is the Roche radius, you expect this to be twice the Roche radius. This argument was first put forth by Ford and Mazia. And so it agrees quite nicely for the inner boundary of the hot Jupiter. Yes?
You want to practically like the masking plotted other things, wouldn't you?
I plotted everything. I mean, it just goes down to 0.1. I mean, there's more below, but this is everything on exoplanet.org. No cheating involved. Well, oh no, transiting. But by now, transiting is. I was actually surprised when you look at exoplanet.org. RVs is a tiny fraction of these. It's amazing how many masses and radii are from transits. So this is basically most of the things we know. It's also curious. Incidentally, there are a few planets here. Yes. So these are ones with measured masses. I know that it's amazing how many there have measured masses. It's easier to measure masses of giant planets, of course, than the sub-Neptune ones. I was surprised that there's so many measured masses. Okay, so now these were scenarios 2, 3, and 4 that I was talking about, which give high eccentricity migration. So I'll do Kozai super fast because we've seen this also many times. So just to very quickly remind you what Kozai is you have a stellar companion, it is stellar binary, and then the planet is highly inclined with respect to the stellar binary. If you start the planet highly inclined with respect to the stellar binary like this, planet like this, then and you started off the planet on a circular orbit, then its eccentricity grows at the expense of the inclination. So the inclination can decrease, and the inclination and the eccentricity will increase. You can go from 0 eccentricity to big eccentricity quickly. That's the famous Kozai effect, or Kozai Lidov effect. One point I'd just like to emphasize is that you need very high inclinations for this to occur. So if you're starting a planet off at 3 AU, and you want to get its peri to be close to the Roche radius, or really you want it to end up on a 3-day orbit, you need its eccentricity to be very big. And to get eccentricity to be very big through Kozai, you need a high mutual inclination. So the relative orientation of the star and the planet has to be very high, 85 degrees. So it's possible that some stars are basically perpendicular to the planets. When you do a more detailed numbers, it seems like this can explain around 10% of the hot Jupiters. So this number that I'm quoting, 10%, is based on sort of order magnitude arguments, but also there's a recent very nice paper by Anderson and Lai from Cornell, where they do very detailed models of the Kozai mechanism, and they do suites of simulations. They include all kinds of effects, and they basically get 10%. It's consistent with not 0.5% of all stars having hot Jupiter, but 0.05% hot Jupiter. And that's just and that's assuming that the orientation of the stellar binary is completely independent of the orientation of the planet, which may be true. Yes.
Is it possible to get to high densities because of octopole term?
So let me. I'll say a brief. So I'm not going to talk much about that. But one comment I was going to make is that this is all what's so-called quadrupole, which is true when the companion is circular. If the companion is eccentric, you have a less severe constraint on the initial inclination, but you need a very extreme eccentricity of the star. So you're trading off the rarity of having perpendicular orbits for the rarity of having an extremely eccentric star. And again, in this Anderson paper, they include this octopole term, and they include possibilities for eccentric stars, and they still get it's around 10 times too little. Actually, it's a little unfair of me to be criticizing the Kozai mechanism just based on this Anderson paper, because they do a much more careful job for the Kozai mechanism than anyone has done for any other mechanism yet. But yes. Well, so it's, so the problem with that is that the high obliquities tend to be correlated with hot temperatures. So there's that effect. If you just focus, so I don't know if you want to focus on the hot stars, the cold stars. Another problem is, I'd say maybe a slightly more severe problem, is from this Anderson paper, the Kozai actually tends to produce obliquities that are symmetrically peaked at the Kozai angle. In other words, they get about as many as plus 45 degrees as minus 45 degrees, and that's not seen in observations. I'll show you the observations towards the end of the talk.
What about stars in eccentric, somewhat eccentric?
So that doesn't help much. You need basically to go over the Kozai bump. I mean, they do this all in the calculation. But so I don't think the initial eccentricity helps much. So it doesn't depend much on that. It's like an order E squared correction. So you need a very high E to correct that. Yeah. Okay. So you have left. Yeah.
What happens to the stars then?
The stars just go. They don't participate in the dynamics. It's just the planets participating.
So should we observe stars?
That's right. Yeah, stellar companions. There are actually some hot Jupiters and some forming hot Jupiters, things with high eccentricities that do have observed stellar companions. So at least two systems, I think there's rock solid evidence that those are being caused by stellar cosi. They see the companion, they see the sun, the planets at the right inclination. So for those, it's rock solid evidence. And then when they look for companions of hot Jupiter, some of them do have stellar companions.
Sorry, let me ask the question differently. What about all the ones that don't have stellar companions? Could the star be lost?
How do you lose a star?
I don't know.
And so the star has to be
Another
fairly
star
close.
passes by.
Well, this star has to be fairly close. It could
how
be.
do you explain all the high Jupiters that don't have a stellar companion?
Well, that's the rest of my thought. So I'm setting this up for. I mean, under this scenario, well, okay. So I guess in principle, they could all, I think, have companions that are just too dim to have been seen by previous surveys. So there are some. Well, they have pretty low limits on some of them. I think a more severe, a different problem is that if you have other planets in the system, that easily kills off cosi because the two planets interact with each other, and that prevents the interaction with a different star. Some of the hot Jupiters, well, this is sort of spoiling the punchline, but some of the hot Jupiters do have farther out companions, and that would kill off cosi. So those almost certainly could not be produced by cosi. Yes.
I'm not aware if this kind of multiplicity concerning stellar companions is also a function of time because of the evolution of those stars and clusters. So when stars form in star clusters and then they dissolve, would you expect that there are some hot Jupiters which formerly had companions and now lost because it is normal kind of evolution?
So the star has to be fairly close. So I think it's difficult to lose those stars. I think it has to be like 4,000 AU. So it's a fairly tight star. So those guys are hard to lose. But it's true. Okay, it's possible to lose stars. But I mean, my main argument against it is not observational, based on the companions. Though. It's based on just the numbers. Yeah. And I think even RAM starting with a 0.5 doesn't help much, because you rely on this based on the shape of the cosi curve. You rely on getting to extremely high eccentricity, and that's the shape of the tracks in the EI plane are basically determined by the mutual inclination. Not positive. I have to double check. Okay, so that was one high eccentricity mechanism. It helps somewhat. Okay, maybe I should discuss it. Maybe we should work it out after. I know it's an order E squared effect at low E, so it has no effect at low E, but maybe at 0.5 it could be. Okay, so the next, another way to get high eccentricities is through planet scattering. And so the idea is you just have a planet that forms near another planet, and then they scatter each other. Violently, they scatter each other. One of them happens to have a small periapse, and then tides act to circularize the orbit. So what I'm going to be describing is a bit of I guess a twist on this, which I call secular chaos. I'll be discussing this in a lot of detail. So it's similar to the planet scattering scenario, where you have planets interacting, but instead of strong interactions between the planets, you rely on weak interactions. So that now I'm thinking of the planets as widely separated, factors of 2 or more in semi-major axis. And in that case, they gradually, it's not, in planet scattering, it's usually thought that they come within the Hill sphere of each other, and then they can give a huge kick to the eccentricity. But in this case, it's much more gradual, and you can have gradual wanderings of eccentricity until the eccentricity gets very big and it comes close to the star. So the motivation is for considering the secular chaos as opposed to the planet scattering case is that if it's the actual scattering of the planets, the initial conditions are, in other words, if the planets come into each other's Hill radius, that means you've started off the planets in a very unstable configuration. And it's hard to see how you'd start off planets so close together where they scatter each other violently. After all, these planets form in a dissipative gas disk. They probably form on cool, sort of circular-ish orbits. And so how do you get in a state where they cross violently? Another consideration is that in planet scattering, if one planet comes within the Hill sphere of another, you expect sometimes it can have a very small periapse because its E changes suddenly, so it comes whizzing by the star. But if it comes whizzing by the star, tides won't capture the planet because tides are actually quite weak. So Boas mentioned this. In order to capture a planet, you need its eccentricity to very gradually increase. So you need its periapse to very gradually fall, sort of on a time scale of at least thousands of orbits, or tens of thousands, even tens of thousands of orbits. And so tides gradually has a chance to act and circularize the orbit. If you try to shoot it in, tides isn't fast enough to act. So one more motivation of talking about secular chaos is because secular chaos happens in our solar system. So Scott showed a picture similar to this. So this is a set of simulations by Lascar and Gatineau. So what they're doing is they're simulating, this is an n-body simulation of the solar system. And they're plotting the y-axis is eccentricity of Mercury versus time. And each of these colors is a different simulation where they move Mercury's initial semi-major axis. They vary it by a few meters. So that's actually within the observational uncertainty of what we know about Mercury. So if you just move Mercury by a few meters, you get all these dramatically different outcomes. So this is a clear indication of chaos. Mercury is chaotic. In around 10% of the simulations, Mercury has a huge E. It actually falls into the sun. Around 10% within 5 billion years. And sometimes actually it even collides with Venus. So it could be dangerous. This is not numerical effects, yeah. Lascar is extremely careful and check this in detail. Many ways of checking this. And actually what I'm going to show, so now I'm going to actually shift gears a bit. I'm going to talk about secular chaos, and I'm actually going to focus on the solar system. So I'll describe how this comes about. Part of my motivation is to show how secular chaos works. Another part is just to teach you a bit about secular theory, which Scott did a bit, but I'll do a bit more. Okay, so let's take a step back. I'm going to work back up to secular chaos in the solar system before going back to the hot Jupiter. So what is secular theory? This is a cartoon movie of, I'm going to show a cartoon movie of secular theory. If you have two planets going around a star, the interactions between the two planets are quite complicated, right? They interact often in conjunction. But if the planets are pretty widely separated, as they are in the solar system, then you don't care about all the kicks each orbit. You can average out the effect over the whole course of the orbit. So this is a cartoon movie. You can smooth out the planet's mass over the course of the orbit. And just look at how the average orbit of this planet interacts with the average orbit of that planet. And that's what secular theory is. So what secular theory will tell you, it will tell you how these rings move, how the rings precess due to each other, and how their eccentricities change due to each other. So that's the cartoon view of secular theory. And so now let's do a real Hamiltonian theory. So what I'm going to do first is let's do secular theory of two massive planets. I'll just call them Jupiter and Saturn. And I'll assume they're coplanar for now. So let's go back to Hamiltonian dynamics. So in this problem, two massive coplanar planets, there's 8 degrees of freedom, right, which we can call the A lambda E omega of all of them. And hopefully we now all remember what all these are. And we also have the outer planets, have those 4 variables. So in secular theory, remember we average out over the position of the planet over the course of its orbit. So you average up the lambdas and lambda primes. So you take the Hamiltonian, average it up over lambda prime. So these lambdas don't appear in the Hamiltonian. And therefore that automatically tells you that the momentum conjugate to lambda, which you may recall is A, or really the square root of A. So these momenta must be constant from Hamilton's equation. So that's a really nice, great simplification, and we can knock off all these variables, all the A's and lambdas. Those don't participate anymore. A's are constant, lambdas are averaged out, and we just have 4 variables left to consider. And of course, physically, these 4 variables are just the orientations of the two. E and omega is just the shape of the ellipse and the orientation of the ellipse. So those are, this tells us about the shapes of the rings that I have in the movie. Okay, so now let's go back to the Hamiltonian. So this is really the energy. We'll turn into the Hamiltonian. So this is the Keplerian energy of the inner planet, of the outer planet, and the interaction energy between the 2 planets. A's are constant, as I said, in secular theory. So we don't care about these terms. They're just constant, so we throw them in the garbage. And this is our friend, the disturbing function. And again, we write our disturbing function as a Fourier series, as a sum of sinusoids. And if you're Scott, you work out these coefficients by yourself. If you're me, you look them up in Murray-Dermott. And so what we care about is we care about the terms, so the phi's that don't depend on lambdas, right? If it depended on lambda, then when I averaged up over lambda, it would go to 0. So I want to look at all, so these are, in the Murray-Dermott tables, this column is the phi. So I want terms which don't depend on lambda. So this term doesn't depend on lambda. If I set j equals 0, right, then j equals 0, this term goes away. If you recall for what I did for TTV, I was looking at mean motion resonances, and then instead of, we had a j plus 1 lambda prime minus j lambda. So those terms will never, you can never make the lambda go away. But here you can make the lambda go away by setting j equals 0. And the coefficient of this term is f1. That's just a constant, a Laplace constant, so we can throw that away. We don't care about constants. But then this is the main term we're going to be interested in. This is inclination, so we don't care for now. This is a 4th order term in eccentricity. I'll come back to that soon. And then there's one other term in the secular Hamiltonian, which is this. I can set j equals 0. So it's cos omega minus omega prime, and the coefficient is just this, which I've just written here. So this is a very simple Hamiltonian, just these 2 terms. Yes?
Why do we care about high eccentricity? Because we want to excite high eccentricity.
So then you have to worry about high eccentricity. So this is, so for now I'm working at to linear, well, you see I'm expanding the Hamiltonian to 2nd order in eccentricity. That's going to lead to equations of motions that are linear in eccentricity. And you have to worry about corrections to higher order in E. For example, for the solar system, that's a pretty good approximation, as I'll show in a minute. So Mercury's eccentricity is 0.2. All the other planets are less than that. So this approximation, expanding to linear order, is probably a pretty good approximation. At the very, very late stage, once you get to E of around 1, then you have to worry about something else. You have to worry about nonlinear terms. But as you also saw in that plot, it shouldn't come back this far. In this plot, the eccentricity is actually during the instability. To understand this instability, they stay within like 0.5, and then only at the end they zoom up from 0.5 all the way to 1. Okay, so this is a Hamiltonian. And so I'm going to, instead of E and omega, I'm going to use my beloved complex eccentricity. You'll see it makes things really simple, so much simpler than if you had relied on E and omega. So bear with me and let's use complex eccentricity. So just to remind you, the absolute value of complex eccentricity, complex number is the eccentricity, and the complex phase is the orientation of the ellipse. This one number encodes the shape and orientation of the ellipse. And then it's trivial to rewrite the Hamiltonian. I just replace E with absolute value of z. Cos omega minus omega prime is this star, right? It's just obvious. And then Hamilton's equation has this very simple form for the complex eccentricity, which is the rate of change of complex eccentricity is basically dh dz star within a constant. And it's easy to take the partial derivative with respect to z star. Right? This has a zz star here. So the derivative of this becomes f2z. This is this term. And then the only other z star is over here. That becomes the f10 over 2 z prime. So for fun, you could try doing all these manipulations I'm going to do without complex eccentricity, and you should get the same answer. It's quite simple. And just to remind you where this comes from, very briefly, so this is, I just postulated this now, but I described it a bit in the last lecture. And just to say, to give a, to show all the scaffolding that goes into building this, where this comes from is I'm using what Scott was calling the Poincaré, or people in general call the Poincaré canonical variables, which is the q is minus omega and the p is this combination, which is approximately equal to e squared. So that you can think of the p is basically e squared and q is omega. And then I'm using what I'll call the Ogilvy trick, and this is general for any Hamiltonian system. If I have a p and a q, I can form this complex number w, and the Hamiltonian equations all become in this nice compact form. dwt, this is dh to w star. This is actually first invented, as far as I know, by Strokey in '66 for work related, nothing to do with orbital dynamics, but with quantum mechanics. I have no idea why Ogilvy was reading. Ogilvy was reading a paper from 1966 on quantum mechanics. But anyways, so I guess you could Google it. Anyway, so this form of the equation is basically this form of the equation, but I'm just throwing all these constants into here. Clear? Okay. So that's the scaffolding, but I have now the dz dt equation is this plus this. So it's a linear, and this right side is linear in z and z prime. So I can write the dz dt equation as this matrix for z prime, right? And I can do the same thing for z prime. The important thing from this equation, this is the full equations for the secular evolution, the two massive planets on co-panoramic. The important thing is, first of all, it's a linear equation in z prime, and there's just a constant matrix in there. These are all constants. Let me just go through it. Everyone should know what all these labels refer to. So n prime is the mean motion of Jupiter, which is of the outer planet. So prime refers to the outer planet. So these are all very standard notations. So n prime is the mean motion of the outer planet. A is the semi-major axis of the inner planet. F2 is a Laplace coefficient, it's just a constant. And the only other thing that's relevant is mu prime, which is that's Jupiter's mass in units. The outer planet's mass in units of the mass of the sun. Okay, so we know what all these numbers are. We can look up what F10 is or stick it into Mathematica. There we go. And it's trivial to solve this, right? The solution is just two normal modes. So it's a linear equation, so we just have two normal modes. Just diagonalize it, solve it, and it's trivial. And I won't show you the solution because there's no need. Sorry. Okay, and excuse the Russian. This is what I found on the internet last night. So this theory for the secular evolution of two planets can be trivially extended to 8 planets or infinity planets. Right? You just, instead of having a 2x2 matrix, you have an 8x8 matrix. So for the solar system, where you have 8 planets, instead of having 2 normal modes, you have 8 normal modes. And it's very trivial to solve. It's called Laplace-Lagrange theory, because they were the first guys to do this. And to be technically correct, they actually include, in usual Laplace-Lagrange theory, they include some resonance terms.
Do you ever guarantee that the matrix you showed before, or the generalization to an arbitrary number of planets, will always be diagonalizable?
Yeah. Well, one of the things I'll say later will actually be able to prove it, but I'll need a couple more steps to prove it. But basically, yes. It's, the eigenvalues are always all real. So it's even more than that. So it's symmetric. It's a symmetric matrix. Basic reason for that is conservation of angular momentum. So. Okay. So this shows the solutions of the Laplace-Lagrange equation. So this is, you can all read this even if you don't know Russian. This is the eccentricity of Mercury. This is over millions of years, so 2 million years. This Mercury eccentricity just oscillates up and down. It's a sum of 8 normal modes. Really only a few normal modes are important for each planet. So Mercury is participating in some normal modes. There's Venus, Earth, Mars goes up and down. You see Jupiter and Saturn have very fast oscillations because they're coupled tightly to each other. So it's very simple. So the whole solar system just acts like normal modes, which is like a bunch of oscillators. So a couple of comments. So I just did eccentricities. For inclinations, the inclinations to this order, to linear order and eccentricities, and linear order and inclinations, they decouple from each other. So you just have a second set of equations, linear equations, for the inclinations. And you have another set of normal modes for inclinations. This type of behavior for Earth, so this is Mercury, Venus, Earth. The eccentricity is going up and down for Earth. That's largely responsible for Earth's climate cycles, which are on million-year timescales. It's Milankovitch cycle. For two of the 3 main Milankovitch cycles are due to these linear oscillations. We can see it's at 0.05. And based on that previous slide, and the claim that the eigenvalues are real. I've already just proven for you the stability of the solar system. I've proven for you that E can't, sort of proven for you that E can't go above this. You can just calculate, because since the solution of these linear equations are just a sum of normal modes, we can calculate the normal modes, and we can see how high the E's will ever go, right? So we can solve the system exactly. It was actually, well, so Laskar, I heard Laskar say that this is the first, the reason why eigenvalues and eigenvectors were invented was in order to solve this particular system. I've never heard confirmation of that claim, so it may or may not be true. It would be neat if it was true. Okay. Okay, so I just said that we've proven the stability of the solar system, and of course Laplace claimed to prove the stability of the solar system. But the solar system is not stable. So what went wrong? Any suggestions? Okay, so you might think it's fourth order corrections, but look at the eccentricity. The current eccentricity of Mercury is 0.2, and we look at all the planets. They're all smaller than 0.2, and Mercury is a little puffball, so it's not going to affect any of the other planets, or hardly. So okay, one possibility is mean motion resonances between the planets, and a second possibility is that the E's are too big, even though the E's are quite small. So just to finish what I was saying with Mercury, so Mercury is going to be, you can sort of think of Mercury as a test particle, so even though it has a high eccentricity, well, okay, I actually don't want to say what I was just going to say. Sorry. Okay, so one possibility is that even though the E's are small-ish, they can still be big enough for nonlinearities to occur, as you suggested. And the second possibility is resonance, that there's more than secular theories involved. And the answer is actually that even it was the first one. It's not resonances. It is all secular theory. And the answer is that nonlinearities are important, even though the eccentricities are small, around 0.2. And the reason why, which I'll show in gory detail, is because of secular resonances. Okay, so to work up, couldn't understand. Okay, so what I said is, so I said it's surprising that it's chaotic, even though the E's are small-ish. But I'm saying the reason that it is chaotic is that even though the E's are smallish, nonlinear corrections still do play a role. And the reason nonlinear corrections play a role, even though these are smallish, is because of secular resonances. It's just, if you don't understand that, you will understand it in 10 slides, I hope, or else I fail. Okay, so I'm going to work up in a number of increasingly complicated situations, cases. So you have to follow each one to get to follow the next one. So you should pay attention. Okay, so the first simplest case I'm going to think about, just do a number of simple secular theory problems. First I have Jupiter is going to be on a circular orbit. I'm going to throw away Saturn for now and put Mercury. Mercury is now just a test particle, a massless test particle, in the gravity field of Jupiter. And let's see how Mercury's orbit evolves. Jupiter is fixed because it's the only mass in the system. So it's just on a fixed circular orbit. Okay, so let's solve it. So these were our secular equations for ZZ prime, inner planet's eccentricity, outer planet's eccentricity. In this setup, it's trivial to write how Mercury evolves. We just take dz dt as the top line, is this term, f2 blah 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 times z, that's this. And then I threw away this term. So why did I throw away that term? No. That's not why I threw it away. Because this is mu prime of Jupiter, this is mu prime of Jupiter. But Mercury is being forced by Jupiter by both these. So why did I throw away this? Z prime is 0. So I'm taking a circular Jupiter. So, okay? So we just have this term. So this is a very simple equation. These are just constants which we can actually evaluate for Mercury. And so this is, you can write this as the mean motion of Mercury, which is around 88 days, I guess, a little less than a year. And then, so it's the frequency of dz dt is basically Mercury's orbital time, but it's reduced by these two factors. It's reduced by one factor due to mu prime of Jupiter, Jupiter's mass ratio, which is around 10 to the minus 3. And it's reduced by this other factor, which is the semi-major axis ratio of the two planets cubed. This is a natural factor to appear because this is just the quadrupole, right? We know it's the quadrupole force that's causing this. It's the mu a cube. And so the time scale is around 500,000 years for this, and that's why Mercury's evolution is around 1 million years. It's the mu a cubes which are giving the time scale. Okay, so I'm going to just take away this time, just rescale the time into this unit. It's just a constant, so we can rescale time and measure time in units of that characteristic time. And our equation motion is pretty simple, very simple. So it's a high school level equation, so even I can solve it. So we have, the solution is z is just a constant times e to the it. So what does that mean physically? Remember z was e to the I omega. The absolute value of this is the eccentricity, and the absolute value of this is a constant. So Mercury's eccentricity is constant, and the phase is omega, which is linear in time. So the phase is precession, the omega is precessing. So all that happens is Mercury has a constant eccentricity, and it just precesses. This is as familiar as the precession of Mercury. You know the precession of Mercury due to GR, hopefully, but actually the precession by the planets, including Jupiter and Venus, is about 10 times greater than the precession due to GR. We can also, by the way, figure out the answer to Scott's question: are there hidden planets inside of Mercury? We can figure out the limit. But anyways, so for the next plots I'm going to do, instead of making a movie like this, which is kind of annoying to make each time, we can make a movie of the z. I'll make the z in time. As this precesses, right, z just has a constant amplitude, and its phase goes around the center. And actually, rather than make a movie, I'll just show pictures like this. So this circle is Mercury's eccentricity over the course of its precession. And it doesn't have to have this eccentricity. I can also choose Mercury to have this eccentricity or this eccentricity. And so all Mercury's orbit does is just precesses with constant eccentricity on one of these circles. Makes sense? Okay, so now the next twist, my second case, is going to be allowing Jupiter to have an eccentricity. Jupiter is now in a fixed orbit, but it has some eccentricity. And so that was that term that I was saying, why did we drop that term? That's this term here. We now have, it's proportional to Jupiter's eccentricity. And the proportionality factor is just it's around 0.1. It's not so important. This is just a constant number. So now we still have a very simple equation. Instead of a homogeneous equation in z, we have this inhomogeneous term. So we have a free solution and a forced solution, or sometimes called a homogeneous solution and particular solution. So that's the general solution. And we can plot again the contours in z of the different orbits of Mercury. So the only difference is before all these circles were centered on the origin. Now all these circles are centered off the origin. To understand what's going on, maybe let's look at this particular point. This is the most, this is a special point. This is the fixed point of Mercury's orbit. And so when Mercury is, if you choose Mercury to have this particular eccentricity and omega, what that means is, so Jupiter had an Jupiter orbit was like this. And then there's a particular orbit where Mercury is aligned with Jupiter and has just the right eccentricity to stay there forever, not to precess. That's called the forced. That's the forced eccentricity. If I start with that situation and then magically change Mercury's eccentricity, all it will do is execute oscillations around that forced orbit. I'll say, just to connect with my last TTV talk, I was talking about free and forced eccentricity. The free is the same as I was talking before, but this forced is a different forced eccentricity. In general, so the last forced eccentricity was the resonant forced, and this is a secular forced eccentricity. In general, you just have, the forced is just the sum of all the forced. And then you have one degree of freedom associated with the free eccentricity, or related to how big the size of each circle is the degree of freedom.
Is the center of the circle on the left side?
Okay, so why is the center of the circle on this side? It could actually be anywhere. The reason is I chose Jupiter's omega to be 0. So I chose Jupiter's eccentricity, let's say here, on this x-axis. So if I choose Jupiter's eccentricity to be here, then these lines would just be oriented like this. That was my orientation. Right. Well,
That's more like, could I have Mercury's pericenter 180 degrees away from Jupiter's pericenter?
Sure.
Still have it?
And it goes around. It's not a fixed point. It's not a fixed point. Its eccentricity, you'll see, will increase and then decrease, and its omega will go around. So there's only one fixed point when it's aligned.
Are you going to mention the order of magnitude
I thought I did, but I should. Well, I didn't fully. So the forced eccentricity is epsilon j, which is Jupiter's eccentricity, which is around 0.05. But it's reduced by this factor, the ratio of semi-major axes of Mercury to Jupiter, which is 0.1. So it's around, I think Jupiter was 0.05. We had it in the plot. So it would be around 0.005. So it's quite small. Compared to the free eccentricity of Mercury, we saw is around 0.2. Okay, so now we'll go to case 3. Well, I'll up to case 5, maybe 6. Okay, so our next twist, what we're going to do is we're the same problem as before, but now we're going to force Jupiter to precess. We're just forcing it by hand, by God now, to precess. Of course, in real life, it's participating in these normal modes, so it's precessing because of that. But now just we're putting its precession frequency by hand. Okay, so the only thing that happens is that this was the term in the equation for Mercury Z that depended on Jupiter Z. So if we're forcing it to precess, Jupiter Z just has an e to the I omega jt here. So this is just an enforced precession of Jupiter, right? Forcing Jupiter to go at omega j. Is that clear? Okay, and then this equation is as trivial to solve, tiny bit less trivial. You have the same free solution, and the forced solution is basically the same, except you have a resonant denominator. Remember that my 1 refers to the frequency, the free precession frequency of Mercury. Remember this 0.5 million years, which I'm setting my units of time to be 0.5 million years. So this is a resonant denominator. It's the difference in frequency between Mercury's free precession and the forcing precession by Jupiter that I'm forcing to precess.
So if you force Jupiter to precess really faster than Mercury's free precession.
Yeah, so then this is the answer. This is the general answer. You can just put it in. So if it's exactly equal, it goes to infinity. We can actually look at the whole contours. So all it does to this plot, it doesn't change the circles. The only thing it changes is the origin, is where this center is. If I start taking it close to resonance, then the centers will be way off to the right. So it's nothing much interesting. Even though it's resonance, you might think, oh wow, it's dangerous. But not a whole lot happens when it's on resonance. The circles just shift here. In a sense, something sort of dangerous does happen. That if let's say the circles were centered here, and I started off Mercury with this circular orbit, then it would go around this resonant point. So it would go from a very zero eccentricity to very high eccentricity and then come back again. Yes?
What are the units of omega j?
So it's frequency.
Yeah,
So this is frequency, and this is the frequency where remember I normalized all my frequencies to units of the Mercury's free precession frequency. So everything's in, so really it's dimensionless. You could say it's dimensionless. Jupiter's in units of Mercury's free precession. Okay, so again,
Of course, you can compound the eccentricity so much that your assumptions break down.
I think that's case 4. Okay, so case 4, now we get the fun stuff. So now we now include nonlinear effects. And the most important nonlinear effect, you can just go in that table of Murray-Dermott that I showed you. And remember I pointed out the e to the 4th term there that I said we'll come back to. So that e to the 4th term, that's the most important term. You can stick that into the Hamiltonian. And remember, when I go from the e to the 4, from the Hamiltonian to the equations of motion, I take a derivative with respect to eccentricity. So it changes the e to the 4 to e to the 3. So I get this term and e to the 3 term. That's the nonlinear term, and the e to the 4. That's the only that's the main correction due to nonlinear effects. Okay, and so let's. This is harder to solve exactly, so I'll just show you what the figures look like. Before I show you the figures, I'm going to replotting what happens if I ignore this term. So let's ignore this term. This is exactly what I had before. So the linear case is without this term. This is what I had before. And now it's going to be helpful to think about things instead of plotting it in, I guess, Cartesian x, y, to think of the absolute value of z and the phase of z. Okay, so it's the same plot. It's just magnitude and phase. And you see this little loop at the center is just exactly the same as this little loop. If I go up here, let's say at 0.8, then basically I'm on a circle that's around 0.8. It's almost constant magnitude, and its phase just goes around. There's a little bit of a wobble because it's off-center. These circles are off-center. Okay? Okay, so now I'm going to take this, focus on this plot, and now see how it changes when I include the nonlinear term. And what happens is this. So what happens is you get what's sometimes called a cat's eye or a resonance. You get a resonance behavior in here. So this nonlinear term allows you to have I guess what's called the dynamical resonance. I was calling something else a resonance. It's a little confusing in the terminology. But in dynamics, usually a resonance is called these cat's eye behavior. And we can understand a bit why you have behavior like this, why funky things happen up here. So let's look at, these are all Mercury's eccentricities. Right? So if I choose Mercury to have a very small eccentricity down here, then we know its free precession frequency is basically 1. Right? So Mercury's free precession frequency, when it's in this part of the plot, is close to 1. Jupiter's omega j, I chose in this plot to be 0.8. So Mercury has 1, Jupiter has 0.8. As I gradually increase Mercury's eccentricity, then this coefficient is really its frequency. Right? Instead of its free frequency being 1, its free frequency is now reduced by 1 minus z squared. So as I go up in this plot, Mercury's free precession frequency goes from 1, and it drops until it reaches around 0.8. And then it falls into resonance with Jupiter. And so you have a special location where it stays in resonance with Jupiter. And because of the form of the nonlinearity, you remain bounded. The detailed shape is easier to see when you look at the Hamiltonian contours. I've also just replotted this in Cartesian coordinates. You've seen this plot before. Does anyone recall this plot from a previous talk? Whose talk? Whose talk do you see this in? Scott's talk, exactly. So this was actually the same talk that Scott talked about. He wasn't talking about secular when he showed this plot. He was talking about resonant dynamics. It's actually a curiosity that you have exactly the same contours. It's the same model which describes the resonance, which he called the second fundamental model of resonance. It's exactly describes the same, describes secular resonance. So this shows you how secular resonance behaves. If you didn't have a nonlinear term, you'd say if you start close to E of 0, you could go up to infinity. But what the nonlinearities do is they give a bounded region where you have interesting behavior. That's what with the nonlinear terms, that's how resonance behaves. Okay, so that was case 4. Yes?
You can forgo the precession of Jupiter. You could solve this analytically. You just won't have an explicit expression of z as a function of t. You would have t as a function of the z.
I don't think you can solve it analytically. This is an absolute value squared in the z. So go ahead, you can try. I mean, you can't solve it as a function of time. You can solve for these contours analytically. That's almost trivial. Even when, for any case, you can solve it contours. But I don't think you can function a function of time. I don't think you can do it analytically. If you can, show me. Yeah, because it's a complex number, so it makes it a little trickier. Okay, so now this is my final twist. So now I'm adding Saturn. And I'm allowing Saturn to precess. So it's a lot of words, but when I write an equation, it's obvious what I'm doing. I'm just sticking in a Saturn term here. Saturn has its own precession frequency, Jupiter has its own precession frequency. Okay, so what does that look like? So now I can dial up these omega Saturn and omega Jupiters. Remember, this omega Jupiter told me how high this was. Right? Because when omega Jupiter was 0.8, I had to drop Mercury's free precession to fall into here. So first I'm going to choose parameters. To show you what parameters I'm choosing, what I'm first going to do is I'll just throw away this term, Saturn term, and plot you the result from the previous case, case 4, of what it would look like. So if it's only Jupiter in this case, it would look like this. If it's only Saturn, it would look like this. So that's how I choose parameters. I chose these resonances, this band not to overlap with this band. In other words, I chose my frequencies of Jupiter and Saturn to be sufficiently far spaced, so that it allows these bands to be apart. So I haven't solved this equation yet. In order to solve this equation, you can't do anything analytically anymore. You have to put it on a computer. But you can plot similar plots like this. And actually, to be a little technical, you actually have to take a surface dissection. So if you're a little more careful, when I do the full system with full nonlinearities, Jupiter, Saturn precession, all it looks like is this. So it looks exactly what you might expect. It's just basically the sum of this and this. That Mercury could either be caught in resonance with Saturn. Again, these are secular resonances. There's no mu motion. Or it could be caught in resonance with Jupiter, or it could not care about either, depending on its eccentricity. So that is the less interesting case, I guess. But now what I can do is I can adjust. I think I dropped Jupiter's free precession from I increased it from 0.7 to 0.8, so that means I drop this down. And so now the resonances are overlapping with each other. And then, again, these are in isolation, Jupiter in isolation, Saturn in isolation. Now when I put them both together, solve it on a computer, then you get a chaotic band. And the region of the chaos is exactly explained by the overlapping of the secular resonances. You can see, well, so this will be true even if the eccentricities are very small, right? This didn't depend on the magnitude of the eccentricities. Okay. So that was my last case. And to make connection to why Mercury is chaotic in the solar system, I have to add a couple more small twists, but it's basically the same flavor. So when we were talking about real Mercury, you have to worry about not just the eccentricity forcing by Jupiter, but you also have to worry about Mercury's inclination. It has not only eccentricity, but also inclination. And as I said, the inclination modes are similar to the eccentricity modes. To linear order, there's a similar linear equation. So this is the equation. Sigma is what's called the complex inclination, where it's I e to the I omega. It's similar to the eccentricity. There's a linear equation. d sigma dt is minus 1 times sigma. That's the linear equation. If I include the leading nonlinear effects, what happened is I get a term here due to the inclination squared, which changes the frequency of free precession of the eccentricity. And I also get nonlinear terms due to the inclination and eccentricity for the precession rate of the inclination. Okay. Incidentally, this is the frequency of precession of the eccentricity. This is of the inclination. Remember, that means the rate at which the plane precesses. This can be equal to this. These two can be in resonance if I choose my inclination sufficiently high. You can convince yourself. This is a minus 1, this is a plus 1. Choose my inclination sufficiently high. These two will be equal to each other, and that is the Kozai resonance. So the Kozai resonance is just these two frequencies being coupled with each other. That's actually not the resonance I'm talking about now, because that works at very high inclinations, which is not at all relevant for Mercury. Instead, I'm going to talk about, well, that's my next part. Okay, so I'm going to talk about the two resonances. One resonance associated with Jupiter's eccentricity, and one associated with Jupiter's inclination, as I was doing before for Saturn's eccentricity and Jupiter's eccentricity. Yes?
So in the last slide, you say when the two secular resonances are close to each other, you have chaos behavior. So what's the criteria on how close these two secular resonances?
So you need two things. You need both of them to be overlapping and Mercury to be in the right place so that it's in the place where they overlap. Does that make sense?
Overlap exactly?
No, so just within ordered unity. To do things for this, well, I haven't succeeded. I don't think I was going to say I haven't succeeded in doing it better than ordered unity. It's difficult to do better than ordered unity. So you can get the ordered unity effect when they overlap within a factor of ordered unity, and that's when chaos appears. In reality, chaos is quite complicated, and you don't just have, it's either not chaotic or chaotic. You have some local bands of chaos and some parts of regular motion. Just a rough criterion of when chaos occurs is roughly when two resonances overlap.
Sorry, I still have a question.
Okay.
Understanding why the anti-parallel pericentrers cannot see a fixed point. So here's my argument, which is probably wrong. So to me, it seems to me if I consider two rings and they
Actually, could we maybe discuss this after? Because I'm running a little late. But okay. It is true though that they have to be aligned, but we kind of have to. Okay, so now I'm going to go to the real Mercury. And okay, so now we can ask for the real Mercury. What are the modes that are important? One of the modes is the eccentric Jupiter mode, which I've been talking about a lot, which leads to one of the forcing. The other one is actually the inclination of Venus. So the mode not by the inclination of Jupiter as I had in the previous slide, but the inclination of Venus. So the inclination of Venus and the eccentricity of Jupiter. Those two modes is what causes the overlap. So the way I'm showing that in this plot, so here I'm showing, this is a plot of, I'm considering Mercury as a test particle, and I'm saying I put Mercury at any position in A and E. So in this AE plot, what I can do is so aside from what's happening with Mercury, I know exactly how Jupiter is behaving and I know how Venus is behaving because it's independent of Mercury. So I know what Jupiter's precession frequency is. I know what its amplitude is. One slight caveat is that when I'm saying Jupiter, it's actually not really Jupiter. It's the whole mode, right? It's Jupiter. All the planets participate in the Jupiter mode. It's actually the mode which is dominated by Jupiter. It's a slight technicality. You can just think about it for now as Jupiter's eccentricity. Okay, so I can plot in this AE space where our Mercury, this blue band, well, let's first start with the red band. As I adjust Mercury's A and E, fixing omega j, then there's a certain region in AE space where it would fall into resonance with Jupiter's forcing. Okay? If I change Mercury's A, if I move it in A, then its free precession frequency will change. Right? So before I was setting the free precession frequency to 1. In general, I have to actually calculate what it is. So as I change it in A, its free precession frequency will change. And as I move it up and down in E and I, that will nonlinearly change its free precession frequency because of these terms. So what I can do is I can calculate its free precession frequencies with these nonlinear corrections, and I can see where it falls into resonance with the Jupiter mode. Because I know Jupiter's frequency, the Jupiter mode's frequency, so I just see where it falls into resonance. That gives me this line here, where it's exactly in resonance. And then I can also calculate the width of those bands. And anyway, so you see in the band, this red band is the band of where it's in resonance with Jupiter. This blue band is where it's in resonance with Venus. And the current Mercury is around here, so it's right on the edge of chaos. So
why does it have a significantly large eccentricity range?
So because it's chaotic. Well,
that's not current.
So
summed over a large range of time.
That's right. So it's a range of time, and so it's not so well defined of what it's not so, as you go larger and larger, it gets bigger and bigger. Let me show you an actual simulation of, this is just a sort of schematic over, I think it was like 100 million years. So this is a little complicated, but let me just tell you what I'm doing. So these blue points, focus first on the blue points, show Mercury's eccentricity versus inclination. To be technical, what I'm actually doing is it's time averaged E squared over some window, because it varies a lot by the secular effects, and we want to get rid of those. To a short time scale, linear secular effects, we want to get rid of those. So we average them up, and this shows Mercury's time averaged eccentricity and inclination. It wanders like this in a full n-body simulation. If it was exactly linear secular theory, it would just stay at one fixed point. It's E squared, it's time average E squared would be constant, it's time average I squared. So it follows chaotically this orbit over, I think this was around 1 billion years integration. And the black points show this model that I was using, where I just include Jupiter's eccentricity and Venus's inclination mode. I'm just including those two modes and those nonlinear terms. And each point represents a simulation. And I take a whole bunch of simulations. Points here means I take a simulation, the time average E and I stays here, time average E and I stays here. So each point which stays sort of on a grid is regular, is not chaotic. When these points, when you time average them, they just end up all over the place. So in other words, another way of saying it is that Mercury is actually, well, first of all, this actually shows that the chaos of Mercury is consistent with this model, which is caused by these two effects. And also that Mercury is living sort of on the edge of this boundary between chaos and not chaos. Yes?
So this is a billion-year simulation?
For this particular plot, for this particular
So it looks like
yeah.
Mercury is executing in motion with a timescale of many hundred million of years.
Mm-hmm. That's like the Lascar's, remember Lascar's simulation?
Yeah.
Mm-hmm.
Can you give me, I realize that it's the same sort of jumps that, or fluctuations that we see in Lascar simulations, but what is that timescale in the problem? Is there something intuitive that I can...
So you're asking about what's the diffusion timescale?
Where
does the diffusion timescale come from? So there is, okay, so this is, I don't know the answer. There's been a proposal for it, which doesn't give the right answer. So the question is I guess the surprising fact is that Mercury's free precession frequency is around 500,000 years, and the chaotic diffusion time, the time for Mercury to diffuse up to E of 1, is around 10 billion years. There's a big mismatch in time scale. So how do you get from, I guess, a Lyapunov time, a short Lyapunov time, to a long diffusion time? So qualitatively, I think it's due to the fact that it's sort of on the edge of where the resonances overlap. that it manages to live just on the edge. If it was in here, where it's very chaotic, then it would be ejected very quickly. But there's not, I don't know, a better, it's, yeah. It would be nice to have a better answer to that. Maybe a problem for one of you. Yes?
Is it possible for Mercury to wander into the chaotic?
To what?
To wander into the chaotic region.
So it is in the chaotic region. It is chaotic. Oh, is it possible for a Mercury to wander in the chaotic region? So it actually isn't. It is in the chaotic region. So there's more. Once it starts, its E starts changing sort of significantly, then my simple toy model is no longer true, and you have to worry about other modes that are important. The details. This sort of explains how it's on the threshold of chaos, but then explaining the longer term evolution that's harder to do within this model. Yes.
You say that each one of the lines actually with lots of dots, and each one of the dots is a simulation that is basically stationary.
Each one of these dots that lie on the regular lines
Basically stationary.
are stationary, right?
Great. So once Mercury wanders into one of these regions,
So it can't. Well, especially in the
why does it continue and stay there?
well, it can't because here it's regular. It can't go from the chaotic zone to the regular zone.
But you see that in the regular
Okay, I mean, so this is the real Mercury and this is the toy model. So there is a mismatch between the toy model. If I just take my toy model, by toy model I mean just the Hamiltonian that I had in the previous slide, then wherever I start my test particle, if it starts in the chaotic zone, it will stay in the chaotic zone. If I start in regular, it stays regular. I can't jump from one to the other. In real case, Mercury actually can actually move into this region. Well, actually, I would say it differently. Actually, the boundary is just slightly different. There is a zone. If I reduce Mercury's eccentricity, it will become perfectly regular, and you can check it on the computer. So it does become perfectly regular. It just doesn't reach there. It never goes into the regular zone. It can't. Okay, 10 minutes. I'll go sort of quickly or skip some things. So the idea is that we had in Shenwu is to apply this to hot Jupiters, that maybe the hot Jupiters also participate in some sort of secular chaos like this. And so I'm going to show you a simple simulation where I start off with 3 planets, one at 1 AU, one at 4 AU, and one at 10 AU. They have modest eccentricities, so they're well separated, many, many Hillspheres apart. They have modest eccentricities at 0.1, modest inclinations. I should say, to see this process of secular instability, you do need a minimum. You have to have these can't be 0. You can't start with 0 eccentricity and 0 inclination. So you do need a seed. You have to get some eccentricity or inclination, or else from the secular dynamics, everything will stay 0. The question is where this comes from, but maybe I can get to that after. Okay, so this shows an example of it. This shows the simulation. So let's just focus on this plot. So there's the lower line and the upper line is the peri and the apo of this red planet. And you can see in the middle there's the A of the planet. And you see it's extremely constant. So that shows all these dynamics is happening at constant A, which shows that this is secular, well, secular effect. What happens is that in this initial time, Mercury's, I'll call it Mercury, the inner planet, E and I just bounces around with modest eccentricities and inclinations. And then so it bounces around. But then it gradually can explore more and more phase space. And it can go up to this curve to get very high eccentricities and inclinations. So this, okay, so you can, just to restate, so if you have 3 planets, in this case you need 2 forcers. You need our proto-hot Jupiter to have at least 2 companions to have a secular chaos like this, where they're widely separated and you have weak chaos, which takes a long time to grow. Okay, since I'm running short on time, I'll just mention that you might ask, what is this envelope? So what the Mercury's eccentricity inclination is bounded by, that's basically the envelope saying that you take all the angular momentum in the system. Remember, angular momentum is conserved. So if you take all the angular momentum in the system and you dump it, you take it out of the innermost planet, out of Mercury. Take all its angular momentum away and stick it into the other planets. So that's the maximum E and I it can reach. So it's just set by the initial conditions of how much angular momentum you have in the system. And so what's critical is just how much AMD, how much of this angular momentum deficit you start with in the system. That tells you how high your E can go. So this part's a little fast, but I just want to running short on time. So this is just another simulation where now we add tides and we add GR. This is the inner planet's eccentricity. It bobbles around, and then it reaches high eccentricity, and then it comes close to the Roche radius, and then it becomes circularized. And you see it, so it ends up in this zone, which is where the 3-day parallel is. And also its inclination is actually not zero. In the secular chaos, you don't have to have zero inclinations, and you don't have to have Kozai inclinations, 43 degrees. You can have a whole range of different inclinations. So this is a whole suite of simulations showing that it can happen quite a lot, but I just want to show you comparisons with observations. So this is the final semi-major axis that's observed, and the final semi-major axis, this is produced in a simple suite of simulations. So the suite of simulations, I should say briefly, it's 100 runs. It's not at all representative. We're currently working on a much more exhaustive sample. This in no way competes with the Anderson result I was telling you about Kozai. We still have a lot of work to get up to that stage. But this is a simple suite of 100 different sets of 3 planets where I move the outer planet. Look at the final situation when the initial outer planet is a different semi-major axis. So it's a roughly similar pileup in semi-major axis to what's observed. There is some tension that our semi-major axes tend to be smaller. Is actually the exact same tension with the Kozai simulations. I think it's related to our uncertainty of tides. Also for the inclination distribution, this is again the observed inclination distribution. So the red histogram, the green is the observed result, and the red is what we get out of our simulations. So I guess the point is you can have a range of different inclinations out of this type of chaotic behavior.
So it seems like you're under-predicting some high inclination.
But at this stage I don't know how seriously we should be. We're doing gazillion simulations now trying to see under what conditions you get to the stage, how robust it is. The really hard thing of doing simulations with this is the phase space is huge. 3 planets, so it would be nice. Well, we're looking to have solid prediction. Really solid prediction. So in the Anderson case, which I referred to before, where they did the Kozai case, and again, very carefully, for them it's easier to have suites of simulations because there are fewer degrees of freedom. These are their final spin orbit alignments. So as I was saying, they tend to get much more bimodal, more higher and lower, and they point that out as a problem also. But I should also emphasize again that there's this weird thing that hot stars have higher spin orbit misalignments than cold stars, and that remains unexplained, and it could be this whole effect has nothing to do with how hot Jupiters are formed, and it's just stellar physics. Then this is the last point which you were mentioning. So people have looked at, people, especially Heather Knudsen, has looked for companions of hot Jupiters. So most hot Jupiters, as I said, hot Jupiters usually don't have companions, but they could have very far out companions that are hard to see, because it takes a long time to see a far out companion. And usually those companions, if it does have a far out companion, RV people wouldn't, if it had a far out companion and the far out companion had a very large orbital time, and the RV people didn't see a full period, they wouldn't quote that planet, because it doesn't have a full period, so it's not yet a planet in their view. But what Heather Knudsen did is she monitored just the trends of radial velocities. So what she did is she looked at 51 hot Jupiters, and she monitored she monitored them very closely on long time scales. Monitored the star in RV, and so many of these stars just have these long-term trends. So long-term accelerations, which is caused by an outer companion. It's difficult to say whether the outer companion, it could be a close-ish in planet on time that's orbiting on more than a 5-year timescale for these trends. She did detect some planets, like this is a planet. Some of these are linear trends, so there's just a lower limit on the it could be more massive and further away, so it could be a star. But then she also looked direct imaging to have constraints on if it was a star, then you'd be able to see it through adaptive optics. The conclusion was that around half of the hot Jupiters have companions less than 13 Jupiter masses and orbital semi-major axes between 1 and 20. So these would almost certainly not be caused by Kozai, because it's very difficult to, I'd say impossible to cause Kozai. Say almost impossible. Nothing's impossible. Almost impossible to cause Kozai if you have a planet there getting in the way of Kozai. Okay, one other bit of information that we have, which is discriminates between these two high E mechanisms, the planet interactions and Kozai, is that the hot Jupiter masses are slightly lower mass than the typical cold Jupiters. This was pointed out already in O2 by Zucker and Mazet, based on much more limited data. Now that we have so much more data, it's pretty clear that they're lower in mass. If you're thinking about the stellar Kozai mechanism, there's no reason for this to happen, right? In stellar Kozai, if it's a star causing it, these planets are all just test particles. So whatever the mass is, it shouldn't care whether you form a hot Jupiter or not. But in planet interactions, you preferentially excite the lower mass guy for two reasons. First of all, it's easy to click around weaklings, right, as we all learned in grade school. Okay, that's a good enough explanation, I guess. Okay, I think I'll just say very briefly there, the secular chaos could be more general, I think, in planetary systems. It happens in the solar system. I think it's quite likely it happens at least in some hot Jupiter systems. It could be at least partially responsible for the observed eccentricities of planets. The red shows the observed eccentricity distribution of giant planets, and the blue shows what we get in a typical secular chaos simulation. So you have a range of eccentricities. There's also the Earth, Venus, and Mars also undergo chaos, so it could apply to that. I'll just skip the last one. Okay, thank you.
Questions?
Are there any works trying to tell the difference in frequency of hot Jupiters between evolved stars and relatively young stars? Because that could be, because
right.
One takes a long time and disks takes a short time.
Right. So there has been a claim, I think Amaury Trio, that you have more hot Jupiters around older stars. I don't think it was a very solid claim. I might be mixing up the name, and so as of now, I don't think there's any strong evidence one way or the other. It's very hard to see them. If you saw a lot of hot Jupiters around young stars, T-Tauri stars, that would be quite strong evidence against this. And there's been, well, it's rare. I should also, I mean, it's hard to see. It's very hard to see a T-Tauri, hot Jupiter around a T-Tauri star.
Even with transits?
Yeah, because there's so much crap in the way. There's all the disk and one other thing, lots of things I should have said. But one other point I want to make is there's some other systems. There's this WASP-47 that we've heard about. We have a Jupiter and a hot Jupiter, and it has two companions very close to it, two Kepler mass, so sub-Neptune companions. That certainly could not have been formed by this. Couldn't have been close to Kozai. So we're in the horrible situation that there's probably a diversity of mechanisms explaining different hot Jupiters.
Did you say why the predicted eccentricity distribution should be bimodal?
So this was just for this particular simulation. So no. And I think in general it won't be. In this particular simulation, there were two secular resonances. So first it lived in one, and then it moved to the other. Yeah, so I don't think it should be. And it observed it. Well, observed it's not.
Can you comment a little bit about what happens if you had photo evaporation of the hot Jupiters? You know, because some could have started as hot Jupiters and then, lose some of their masses, and then you don't consider them now in your analysis, or, when you show this correlation with the with the lower masses, it can also be because of losing some of the atmospheres.
Right.
So is
Well,
it going to affect this?
So I don't think photoevaporation is too weak, and Ruth has worked on this to affect you lose a very small fraction of the mass. What's more significant is you could get tidal shredding, that when the planets come, well, first of all, as this high eccentricity migration is happening, it comes close to the star star is squeezing it, is dumping a huge amount of energy, that'll puff up the planet. The planet could overfill its Roche lobe, lose some mass that way, and then evolve. And that could change how it moves. It could move in the mass period plane. I know my colleague at Northwestern, Fred Razio, has worked a bit on this and seeing how you can move from hot Jupiters into, it might explain some of the closer in Kepler planets. It's a very difficult problem. Even in stellar binary evolution, where this has been looked at for a long, long time, this how two planets tidally interacting, losing some mass, how they evolve, is very can of worms.
Yes, if you would make frequencies of occurrence of the different processes, what would be the order of magnitudes, you know, for fraction of systems which have been affected by causae, by secular chaos,
so
by migration?
For causae, it's fairly straightforward to do, and that's what this Anderson paper did. There are not so many assumptions that go into it, and their basic answer was 0.05%. It's almost impossible to get, you can read the paper, but it's almost impossible to get it above 0.05%. They have some nice arguments for secular chaos. It's much more difficult. I mean, I'm working on now trying to constrain it. So unfortunately, since there are just so many degrees of freedom, it's hard to have a more solid number. We have a third planet, and you can put it almost anywhere.
What is this point? Sorry, what is this 0.05% exactly of all stellar systems?
If you assume that if you assume that the orientation of the binary is random with respect to the orientation of the planetary system, if we use the observed eccentricity distribution of stellar binaries, and if you use the observed period distribution of binaries, it depends a bit on what you assume for tides, but actually not so much. So it's a pretty robust number, and we also worked that out sort of scaling arguments just based on those numbers I was just telling you. You can sort of estimate that it would be 0.5%.
Okay, so 0.05% of stellar systems with planets can be affected by causae.
Yeah, and I just one more thing. So it's also ignoring planetary companions. So if you have a planetary companion, you would reduce it to low.
Even lower. So that's much lower than the fraction of hot Jupiters, which you showed was 0.5%. So it's at least they're at least 10 times more frequent than what you would expect.
Yeah, and I would say some people do disagree. So some people would say it could be higher. There's other papers by Naos from a few years, but this recent paper by Anderson, I think, it seems it's very careful and thorough. Maybe someone could tweak parameters and get the right answer.
Okay, Yoram, we would like to thank you again. Coffee break, and we meet at 11.